Right. All right, cool. Thanks, everyone. So we're going to go into the age-old question as presented by our Globe friends, how they definitely know the distance to the sun. And Alan's right. This should definitely be in quotes because nobody knows any such thing. It's all ever been Kepler ratios and then trying to guess with different coefficients. So it would start with any good presentation. Starts at Wikipedia, starts with the mainstream definition. The astronomical unit, which is what we're going to try and define, is definitely defined as 149,597,870,700 meters. I definitely know that's how far it is. That's its definition. They've given it an empiric specific value. And as you can see here, historically, it's actually been an average of the Earth's difference, meaning the average of its aphelion and perihelion, or its shortest and furthest points, which is still what it is. Don't get confused. This is absolutely what it still is. Just because they give it a quantification like this doesn't change the actual inherent value and its relationship to the ratios from whence it came. If we look over here, of course, if we go read a little further on Wikipedia, it will tell you that all of this is based on Kepler's laws of planetary motion, which are, again, empirical observations of the celestial bodies only. There aren't dynamic forces. There's just empirical observations of cycles and observations of motions. So this is what we were using to calculate the relative distances of the planets and the sun. Relative distances is all we'll ever have. It's all they ever needed. It's all they have today still, as we'll go through it.
The reason we exist is because you cannot stay ahead of all threats. So what we do is we block by default.
If you look at all the people who guessed or who scientifically hypothesized the distance to the sun, they put it back to the Greek times. They go all the way through here. The one that we're really going to talk about, because that's the one that they make a big deal about, and they kind of hide him in the middle, is Christian Huygens over here, and he was the first one that came conceivably close to the percentage and his guess of the AU. But we're going to go over how he did that, which is in assuming a radius of a different celestial body. And the way that we get the AU turns out actually is heavily reliant on assuming the radius to our celestial body. But they also use parallax angles. And real quick, we're going to go over that. We're going to go over the specific math that they use to calculate the supposed distance to the sun based on Kepler's third law. We're going to go over this diagram over here in just a minute. But if we're going to calculate parallax angles, the AU, which we're going to be defining, we haven't defined yet, actually is important because they're using that to define all the other standard lengths of measurement. Over here, we're defining a parsec. It's defined at a distance which 1 AU subtends 1 arcsecond angle over here. Alan did a presentation on this a little while back to get the units of measurement right. And again, this is a base unit measurement that then gets applied to parsecs, which then gets applied to distance of light years, right? So now we have this unit of measurement, and then you can even divide that further into light minutes and light seconds, and then you have 8.3 light minutes. These are all like derivatives of this relationship based on the AU, which we still have yet to define. And again, back to Wikipedia, these are all the distances that you get from Kepler. None of these are actually expressed in known units. It has the appearance of being empirically sound, and this has the appearance of specificity, but these are in ratios of AU, so 1.52 AUs. And over here, the actual distance is just the average distance. As we went over before, as expressed on that first page, the average of the perihelion and the aphelions, or the furthest and the closest, are just going to be the mean. So they have the list of averages. So none of these have any inherent metric value in kilometers or meters the way we're looking at it. They do it over here. They try to define the radius, which gets a definition, which of course comes back to the actual radius. But all of these distances in yellow are Kepler's observations of empiric value. So these are all just averages and based on Kepler only. Well, we're going to revisit our boy Huygens real quick, one of the third guys to guess the actual AU. Now, this one is talked about frequently because of the requirements that his guess actually required. So he had some prerequisites to that, and that was the size of Venus. To make his guess, he needed the actual size of Venus. Luckily for him, though, he was a practitioner of dark magic and used numerology and mysticism to predetermine the size of Venus to use in his scientific calculation for the determination of the AU. And of course, he was the one that got closest. Now, it doesn't matter that he used numerology and mysticism.
So lucky. That's insane.
It doesn't, to the scientific consensus, it doesn't matter how he arrived via his techniques of numerology and mysticism to the size of Venus. It just matters that he was super duper right.
So the important thing here is that now we're taking the Earth radius that we're using for the base terrestrially for everything, and we've now discovered the same exact unit of length in the sky. Is that what's happening?
Yeah, well, so we've taken Earth's radius and we've supplied that as a base unit for Kepler's measurements of empiricism. So if you get the measurement of the ellipticity of the motion, or from the length of the 30 major axis, if you just want to quantify that in terms of terrestrial radii, that's kind of what we're doing. But so we haven't actually given it an empirical measurement. We just know that, we know how far the radius is, and we're trying hard to quantify that into all of these ratios, which is exactly how they did this. I know we've all seen this meme before. I think it's thrown up by flat earthers to show that, this is how science is done, how they never actually knew the correct distance to the sun. Well, there's a little more to this. There's a math formula called the angular size formula that, when supplied with Earth, with the sun and the moon's actual apparent angular size of 0.53 degrees, you can manipulate the diameter of the said object and the distance of the said object to get back to one uniform system. So these are all actual guesses manipulating 2 of 3 variables in an equation. So they have Copernicus say guessing the distance of 3 million. Haha, he was wrong. Tycho Brahe guessing 13, Kepler 13, Newton 28, and then again at 54, Martin 81, 1995, all the way through. And what they're doing is using this formula, which is just, in this one it's theta, but 2 times the arctan of the object size or the diameter over 2 times the distance. And here's how you would visualize it. And this is how they particularly use angular size in astronomy, or exactly how they got the distance to the sun today, which is 2 times the arctan of the diameter over 2 times the distance, which is this formula over here. Plugging in observable 0.53 degrees, you can see the output actually comes out to one of the ones that works. One of these tuples is 93 million miles away, 864,000 miles wide. So 0.53 degrees is the only thing that doesn't change. And then you can manipulate the distance and the size to get all these outcomes that they would have predicted. So when they're saying, hey, we manipulated the size, we just been using science to guess, and it says no, this could easily have been a backwards derived engineered series of guesses that would lead one to believe of the scientific progress, right? This is meant to hint at scientific progress, but it's just manipulation of this one formula with different distances and diameters until they arrived at a tuple that worked for the rest of the ratios. A tuple is just a set of these coordinates that also work. So you have 0.53 degrees, 93 million miles, and 864. These are the 3 things in red that are being interrelated. These are the 3 actual variables being used over here. So when they say that, they've been guessing, it's, well, no, they've been using this formula. And I would even make the argument that they weren't even historical guesses. They were retcon guesses. They were historically added to contextualize to give the ostensible appearance of scientific progress. That's my opinion, though. Any questions so far?
I never thought a quick shower habit could turn heads like this. It all started when a Boston doc let me in on something nobody talks about. He spilled that there's a tiny hidden switch in a guy's body. Flip it on, and dudes report bedroom energy and drive they haven't felt in years. The wild
Question so far.
This experience reminds me of a hypothetical scenario, like watching a Penn and Teller magic show, where there's like 1,000 people in the audience, hang out. But there's also this one guy in the front row. Every 10 minutes, he stands up, turns around to the audience and says, okay, guys, here's how they did it. For the whole show.
Right. Yeah, it is kind of, they've been putting on a show, and they have this like ostensible veneer of historical vernacular. Like, this just really happened, guys. And it's like, did it? Did it all happen, though? Because it would be real easy if it didn't. And you could easily just say that these people made guesses, I don't know, spread them out along the timeline, and that you can even give it the appearance of an upward ascending specificity towards accuracy. Like, look, we're getting closer and closer and closer. And that's not even what happened. Like, they had guessed all over the place. These are cherry-picked guesses. If you go back to the first list that we actually looked at on Wikipedia, these people guesses like the way off and wide swings all the way through. But when you paint it, like when you're telling the narrative, look how good science works, right? It's like, well, no, if you were to just manipulate these variables, we'd be back where we started. So for the next part of the trick, we're going to go into the math that they use to do solar, to calculate the parallax of Venus to estimate the AU. And we're going to watch an actual astronomy 101 course on 1.25 speed. It'll take about 8 minutes. We're going to watch this course. We're going to watch in the Glober lingo from a Glober class how they teach Globers to calculate this metric. Because in our experience, if I were to tell Globers how the Globers calculate it, I'm instantly wrong. So we'll try it this way, and we'll see if this is any better. Did I share with sound is the question, though.
Negatory on the sound, Ghost Rider.
Okay.
That is my favorite modus operandi, of course, and I'm sure everybody can hear it coming. There is no greater pleasure than taking Globy assertion and filling in the blanks in their formulae with the figures they assert are reality, and to actually see what the outcome is. I just love that.
Shared audio. We'll hear Stones and me.
Do we have audio?
Yeah, that's echo.
Okay, so I did. All right, so get rid of that. That's not going to work. Share again. Brave window. It said tab audio.
Not Brave.
Yeah. Hey, actually, I don't agree with that. Whatever that was.
Yeah, don't be Brave, man. I use it right now, man. I'm looking at you through Brave right now. No problems at all.
Gross.
No problems at all.
Okay, now I think I got it. Like it's certainly, like, if it was Linux, this problem would be magnified and worse. That's all I'm going to say.
No, I don't know what you're talking about. I can still hear that echo.
Can you, though?
Yeah.
No. Really?
Yeah. Both of us.
Well, listen, just don't talk for a minute. I don't know. This is the last combination of settings that I have.
Yeah, you're good. So just send it.
Please go away, bar. All right.
Check the volume slide on video.
Well, the one thing Kepler did not
All good.
tell us was the absolute size of the solar system. He tells us the relative size. We could take the planet Mars, for example. We know its period is such and such. We plug it into Kepler's third law, and out we get the semi-major axis in astronomical units. We don't know how big an astronomical unit is. We just know it's the distance between the sun and the Earth, but we don't know what that distance is in something meaningful, like meters or kilometers. So we can say that Mars' semi-major axis is 1.6 times that of Earth, Jupiter 5.2 times that of Earth, or whatever the numbers happen to be. We understand the relative scales and distances and spacings of the planets, but we don't know the scale absolutely. And to do that, we have to actually measure one astronomical unit, the Sun-Earth distance. So we're going to take an aside here and talk about two ways in which this was done. One, very early on, using parallax measurements of Venus, and one, a more modern-day solution from the 20th century, where we actually send radio waves out there, but the radio waves bounce off of Venus and come back, and we measure time of flight. So again, Kepler gave us the relative size of the solar system. Now we're going to figure out the absolute size. And to do this, we must measure 1 AU. So let's take the case of Venus. It's the planet that gets closest to Earth. And here it's drawn in that configuration of closest approach. We have Venus's orbit, which is at 0.73 astronomical units. Again, we just figured that out by measuring its period. How long does it take to go around the sun? Stick it into Kepler's third law. Kepler's third law tells us it's at 0.73 astronomical units. Kepler's law tells us that we're at 1 astronomical unit by definition. And so sometimes Venus is very far away from us, sometimes it's close. Here it is at closest approach, and at closest approach it's 1 AU minus 0.73 AU, so 0.27 AU. At different positions in its orbit, it would be different numbers of AU, but let's consider this configuration, because it's kind of the easiest to deal with mathematically. So if there's some way that we can measure the distance between Earth and Venus at closest approach in actual units, something like meters or kilometers, then we can figure out how many meters or kilometers are in 1 astronomical unit, and then we know the actual absolute physical distance to everything else orbiting the sun, because we already know those distances in astronomical units.
All we need is this one thing, guys, and then we know the distance to everything everywhere forever. Isn't that neat?
Remember this frame, okay? I'm going to refer to it when we're done here.
Okay. Method 1 is parallax, and we'll get to work an example of parallax calculation now. So we looked at this figure before. Imagine that you have telescopes on opposite sides of the Earth, which Skynet has, for example, and you're looking at Venus. And we'll now suppose that that gray object, instead of being the supernova, the comet that we talked about before, or the moon as it's referred to in the textbook, we'll presume this is Venus. And if we look at Venus from one side of the Earth, it should appear around a certain set of stars, distant background stars. And if we look at Venus from the other side of the Earth simultaneously, it should appear around different stars. There should be a shift.
Thank God we know the distance between those two.
So what I'm going to do is I'm going to turn this figure on its side. So I'm going to rotate it clockwise. And we're going to go through this geometry. Now, this is a geometry that we'll encounter over and over again in this course and in the lab. You can use this for many different things. You can use it to measure angular sizes of objects. In lab 2 that you're approaching, we'll use it to measure the size of the Earth, all sorts of things. So this is going to be very familiar geometry, particularly if you're in the lab course, you'll see it double. But here's the basic idea. What we have here on the left is Earth, and here are the 2 points of observation, one on one side of the planet, one on the other side of the planet. The distance between them, we call that the baseline, that's the distance between the observing points. A class ago, we did the
We also call that the diameter of Earth, which is 2 times the radius. So that's all they're using.
and it's also the opposite side. We're talking about the big triangle here.
Stone, it's echoing when you talk. It's not worth it.
Is it? It's good for me in the stream, I think.
It's not good. It's not good. We interact though.
That's not good for the stream. Okay. All right. Nope.
You experiment with the finger, where you put your finger in front of your face and close one eye, and then shift to the other eye. Your 2 eyes, the distance between your eyes is the baseline in that example. And you're looking at your finger, and that's the distant object. So in this, we're measuring the distance to Venus. So the gray dot over here, consider that on Venus. Nothing's to scale. If it was to scale, the angle would be very, very small. It'd be hard to fit all the numbers and letters on here and the arrows. So it's not to scale. But imagine we're looking at Venus from 2 sides of the Earth. So if we're looking from the bottom part here in this figure, Venus would appear over in this part of the sky. They're background stars, and it would appear to be near them. If we're looking at Venus from here at the exact same time, it will appear to be in a different part of the sky. It will appear to be over here compared to the background stars. And we can measure that angular shift. And we're going to call that angular shift theta. And so I'll write this down here. Theta is the angular shift as observed from one side of the baseline to the other. In this case, we're talking Earth baseline.
Just a ratio.
And for Venus, it's about 1 arc minute, approximately 1 arc minute. And 1 arc minute is what fraction of a degree? 60th, yeah, 1/60th of a degree. And if you remember, 1 arc minute is about as good as you can do without a telescope. So once you introduce the telescope, this is a very easy thing to measure. Stars, when you look at a picture and there's stars in the picture, the stars tend to be blurred out to scale of 1 arc second due to atmospheric blurring effects, the atmosphere shifting around and blurring our image. 1 arc second is a 60th of an arc minute. So an arc minute is like 60 stars across if you line them up side by side. It's a very easy thing to measure once you have a telescope. So this was a very easy measurement, and that's the observable, but we want to turn this into a distance. Well, the concept is, imagine drawing a giant circle centered on Venus, a circle that intersects the Earth. Here it is going around, goes off, the figure comes back around and back here. So you can think of this as an angle as a fraction of 360, or a piece of the circumference of this big circle as a fraction of the whole circumference. In any circle, you have 360 degrees. This angular shift is some fraction of a full 360 degrees, theta over 360. And that has to be the same fraction as this distance, the baseline, divided by the whole circumference of the big circle. Think of it as a giant pie, and you're taking a little sliver of pie. How much pie are you eating? You can measure it in angle. That angle is some fraction of 360 degrees. That's the fraction of the pie that you took. Or you can measure it out on the circumference of the pie, the crust. I took 2 inches of crust. Maybe there are 20 inches going around. I took 1/10 of the pie. And those have to be the same number. Okay, so let's write it down. In fact, it's written up there, but also right on the dot cam.
Everything you just explained was a ratio. It's the same ratio. There's no empiricism of anything yet.
In fact, I'll do it on a new page. Make some room for the computation. So the angular shift, which is what we measured, divided by 360, is going to be equal to the baseline of observation divided by the circumference of the giant circle. So what's the equation for circumference? Circumference of a circle is equal to 2 pi times the radius of the circle. 2 pi. Well, the radius of this giant circle centered on Venus intersecting the Earth is what? Physically. It is what we want. It's the distance to Venus. So the radius of the big circle is the distance, and that's what we want to know. How far away is Venus, in this case, at closest approach? Okay, well, let's work it out here. We said that the angular shift is 1 arc minute, or 1/60th of a degree. When doing this, often angular shifts will be measured in arc minutes or arc seconds. When using this equation, you have to convert that to degrees. The units must cancel out. But keep that in mind when you do your homework. Whatever's given, like in one of them, I give you an angular shift in arc seconds. You've got to get it into degrees, so the degrees cancel. The baseline is the diameter of the Earth, and it's about 1.3 times 10 to the 4 kilometers, divided by 2 pi distance.
So now we're just ratioing what we know as a known distance, which is just the radius disguised in kilometers. So this is the radius. This is 2 times the radius in kilometers, right? 62,000 kilometers. 1.3 is the actual diameter. 1.3 times 10 to the 4 kilometers. This is just the radius. So now we're only going to quantify based on the units of a circle based on this known radius value, and that's it.
And distance is what we want to know. Well, let's take this. You stick it into a calculator, and you do that. You're going to get a very small number. 1/60th divided by 360 comes out to 4.6 times 10 to the minus 5. And there's no unit. It's dimensionless. The degrees have canceled out. And over here, if we divide 2 pi into this number, we get about 2.1 times 10 to the 3 kilometers divided by the distance between Earth and Venus at closest approach. Now, if you're farther away, you're going to get a different angular shift, and so this would be a different number as well. At closest approach, that's the angular shift, and so that's the distance closest approach. Now, to solve this, we need to solve for distance. So let's get distance by itself, and I'll just go through the steps here. We're going to multiply both sides by distance, and divide both sides by this small number right here, 4.6 times 10 to the minus 5. 4.6 times 10 to the minus 5. And the reason we're doing this is these will cancel out, giving us a distance by itself. Now on this side, distance cancels out. All make sense so far? Just a little bit of algebra, practice in solving an equation. So we get distance is equal to 2.1 times 10 to the 3 kilometers divided by 4.6 times 10 to the minus 5. You plug that into a calculator and you get about 4.5 times 10 to the 7 kilometers. So that's the distance to Venus at closest approach. You can measure it using the parallax technique. Now, why are we doing this other than to have an example of a parallax calculation? Well, we want to know how big the astronomical unit is in something that we're familiar with. And kilometers, we all know what a kilometer is. So let's go to the next level here and let's solve for 1 AU. Now, at closest approach, we already said at closest approach, Venus is approximately 0.3 astronomical units from Earth. So let's write that here. 0.3 AU is approximately 4.5 times 10 to the 7 kilometers. So if we want to know how many kilometers are in 1 astronomical unit, we'll divide both sides by 0.3. Over here we get 1 AU is equal to, you do the math, and it's 1.5 times 10 to the 8 kilometers. That's pretty big. I mean, that's a huge number of kilometers, 1.5 times 10 to the 8. And it doesn't really matter if it's big or small. The point is we need to know what it is. So we know the true distances to everything and the real scale and size of the solar system. Now that we know how far Earth is from the Sun, since we know all the other planets, their distances from the Sun in AU, we now know them in something physically meaningful like a kilometer. Does that all make sense? Is that good?
Nice. And then he's going to go into the other method, which is going to be radio ranging, which we're not quite ready to go into yet. Now, we're going to get rid of this thing so you guys can talk again. I got to share it, Gary. So I got to stop sharing, reshare, presenter view. All right. Should be safe to talk.
So someone's asking in the chat to kind of break this down a little more. Like, how is this physically confirmed, right? Because we're going over the calculations, but maybe to kind of re-illustrate the ratio-based interconnectedness of what just transpired, because it's like you need variables to solve the equation, but the variables are the output of just using other ratios of the base thing and then recomputing that so it comes out to be a number. But is it a physically meaningful number? That's the thing that's in contention here.
Yeah, we're gonna go through that, and then we're gonna compare it to Eratosthenes and how that same approach was used to know how to measure the size of the Earth by knowing distances on the Earth already. Which is not really a good method. Am I sharing here? Did I reshare? Do you have to accept it?
Probably, yes. Yeah.
There you go. So yeah, to go over all that stuff that he just said, all we're using is this relationship of baseline over like two pi times the distance. So we started with 2 pi r, which is just a circle, right? So the only thing that when I said we're still using ratios, it's because he hasn't actually plugged in anything to measure anything. Until you plug in something, this is all just going to output ratios of a circle, degrees, 1 degree, this degree in angular shift. There's no actual metric. You're never going to get a distance in kilometers from the parts of a circle. Only when you plug in one of these knowns, and the known that he plugs in is this baseline, which if this is Earth, this is representing the whole diameter of Earth. So you can only get the distance to the sun by knowing exactly the radius of Earth, so that you can use 2 times the radius to get this diameter, so that you can plug in this baseline distance to get the true distance. So it's all just broken down as the radius. Now, when I looked into this, I was kind of surprised that the value that all of this depends on as like the standard candle, the metric unit of the radius, is the only thing that flat earthers have managed to falsify over and over again with long range observations, laser tests, scientific method put forth, etc. So we know that value is not the actual size of the Earth. So they built this entire model based upon this presupposed radius value, and then it just gets further reified and reified and reified until you have parsecs and light seconds based on a distance derived by that ratio put into a circle with only ever supplied as the radius of Earth. If that helps.
Yeah, no, that was great. And then next you said you were going to talk about how they got the radius of said Earth, because that's the big one that they're going to need to do the baseline for all this.
Right. So again, here's the actual observation that they're using. The baseline distance is this over here, and we know that because of sun angles. We know exactly how big the radius is because we measure the circumference by looking directly at the sun and lining up shadow angles. So this is the quick Eratosthenes example. He did the observation of an angle of a gnomon at the bottom of a well at I forget, it was at the solstice. I was going to say equinox, but it's the solstice when the sun is at its furthest point, and he noticed that there wasn't parallel on the other side, so he did a difference between about 90 degrees, and we got 7.2 degrees of difference between Alexandria and Syene. So of course he had a buddy in Syene or whatever, and they knew exactly what this measurement was at the same time. The only thing that they don't go over is how they knew that Alexandria was 800 kilometers away from Syene. This whole calculation also has no actual meaning until you supply the distance between these two known points. The math over here, 360 degrees divided by 7.2 degrees doesn't give anything. Only when you times it by 800 kilometers does it output anything significant, which is how you get 40,000 kilometers the circumference of Earth. So we're still using properties of a circle to measure things that we're supposedly already knowing, so which is a weird part. Not to mention that the whole Eratosthenes angle doesn't actually prove the shape of the Earth. This could just be the circumference of the sun. We can use the Glober method as presented with the sun angle as it is with the local sun, and we can output the same equatorial circumference, or the distance that the sun travels around the center of flat Earth, which of course haphazardly would be the exact same as it would on a globe anyway, due to this being the only equivalent and the north being much of the same. So that's one way to take it. You can also take it the other way and say, actually, we could do it completely differently on flat Earth, and we can imitate those exact angles. We can derive the radius of a table, right? We did this from decimal z using refraction and having a local light source. You can take the same angles and measurements and known distances and ratios and come out with the same exact output. So let's avoid decimal z doing that same thing. And when we're applying it to what we're talking about with the circumference, right now, this is supposedly how we know the size of the Earth, right? And we determine the size of the Earth by knowing a measurement on the Earth. So if measurements are a ratio of the overall size, and then we haven't measured anything, we've only supplied a known measurement and we've output a correlation with that known measurement. Like if this distance between Alexandria and Syene was different, the output would be different. The circumference of the whole model would be different. This is the driving force. Just like in our parallax example, this is the driving force. Without having this baseline in a quantified kilometers, meters, anything, the rest of this has no meaning and can't be computed.
Well said. And on top of that, another thing I wanted to reiterate was the significance of how Eratosthenes was able to calculate the distance. It was dependent on knowing the distance between the city. And the way that they try to tell these stories is like these units of measurement, a stadia and a cubit, are independent of a meter, right? So it's like he just happened to know, they calculate the actual, known accepted value of the Earth's radius using an entirely different unit of measurement and metric to determine the distance between these cities. And the trick to that is a stadia and a cubit are defined as a ratio of the terrestrial meridian, and a meter is also a ratio of the same exact terrestrial meridian. So scholars only disagree on how much of a ratio they are. So like they teeter between 99.9% of a terrestrial meridian, meaning 0.1 air in Eratosthenes' estimation, or they'll be off by 0.16 of a terrestrial meridian. So it's just close enough within the accepted values of this independent unit of measurement, but it's not an independent unit of measurement. And then they tried to do the same thing later in the 60s and 70s with the speed of light by changing the definition of a meter to the wavelength of, I forget what it was, but it's a wavelength of light at a certain temperature. to use that to define it as a meter, but that's also a ratio of light traveling in a second per inches, which is a ratio of a meter too. So it never actually changed anything, but they've gone out of their way to give the appearance of independently separating these to try and build this historical narrative of how these ratios are physically meaningful and actually represent the dimensions of where we live.
Yep, another layer of the lore they try to get you with. So going back to the parsec and stellar parallax angles to begin with, right? We always go over how to calculate them, but a shout out to our boy Cassander, who showed us that from a geocentric point of view, with stars that move around you, parallax angles are calculated exactly the same. This is in no way proof of Earth's motion around the sun. It could just as easily be used as proof of the star's motion around you. The same shift in the angular shift would be just as they described in the heliocentric model from different points on Earth, would also be observed if the stars were moving around us in the same way. And this is a good meme that exactly shows that inherent similarity, right? They just changed the intersection point and the angles remain exactly the same. And if we overlay the example we were looking at before, how to calculate arc seconds, you can see the similarity. And if you overlay the exact calculation we were using to find the AU, you can see the exact similarity. So that the parallax angles are identical for geocentric position. So nothing about calculating parallax angles proves their model. Just always like to calculate that. Doesn't do a real big difference for changing the ratio of the distance that we're talking about. But whenever talking about parallax angles, I like to show that diagram to make sure everyone understands that the angles would be inherently identical if everything was fixed and they're moving around the observer, as we argue here. Now, that's the parallax portion of the argument. Now we're going to go into the modern technology, radar range finding, and all the inherent modern techniques that they use to claim the same distance.
I think you'll have to reshare with audio.
Yeah.
Unlucky.
Right.
Did you say you were just going to live narrate it?
I was gonna find the spot and then I was gonna reshare. All right, I got it. All right, stop. Cool. Now stop sharing. Reshare. No one talk, I guess. Although, yeah, can't share a tab. Also share system audio. Yeah, there's no way around it to just share Canva audio. All right.
Get the example now. It's a little bit easier to do mathematically, but I want to show you how it's been done for centuries. Then you enter the 20th century and you have technique number 2, which is radar ranging. After World War II, this was possible. And basically, when Venus gets the closest approach, again, it's about 0.3 AU away, rounding off, we send a pulse of radio waves. Radio waves are just another form of light. They travel at the speed of light, bounces off Venus, and comes back. Very similar to the first homework problem we had, where we sent a message to the moon, it came back immediately. So we use the same equation. Distance
you guys hear it now, right?
Speed times time. And the distance that we're traveling is to Venus and back, so that's 0.6 astronomical units. Again, I'm rounding off. The speed of light in kilometers per second is what? To the fifth, that's right, kilometers per second. And then all you have to do to measure what 1 astronomical unit is wait. So they send the pulse out. If the solar system is big, now they kind of knew what the answer was. From the parallax measurements, we know how big an astronomical unit is. But if we had no idea, we'd send this pulse of radio waves out. If the solar system is huge, you might have to wait hours for it to come back. If it's really small, you might have to wait seconds for it to come back. It is what it is. It takes about 300 seconds for it to come back, rounding off. It's about 5 minutes. So that shows you how far away it is. Communication round trip time scale of Venus, about 5 minutes. The seconds cancel. So we have 0.6 AU is equal to a certain number of kilometers. Let's see, that would be 9 times 10 to the 7 kilometers. Divide both sides by 0.6. You get 1 AU is equal to, again, of course, you come up with the same result, 1.5 times 10 to the 8 kilometers. So those are the two primary ways to know how big an astronomical unit is and consequently how big the solar system is.
And real quick, we got one more video because we're going to go through the Glober refutation to this, right? This is a paper from McToon's website that we're going to go over called Radar Echoes from the Sun and how they know exactly the math that we were just going over. And this will be the scientific corroboration for the radar ranging distance measurement that we just went over. And as a method of luck, actually, McToon would just use this paper last Tuesday on his show, and he went over it in exclusive detail. So instead of me strawmanning the Globe again, I'm going to go straight from the Glober's position, and McToon is going to give us the steel man of this paper in 2 minutes or less before we argue against it. All right, everyone plug your ears or whatever.
So prove that it's 93 million miles away. Okay. MC2.net/sun. Here we go. It's been done before. And so here's the write-up. So Not going to read it. Just go to mc2.net/sun.
He never does.
And you can peruse it at your leisure. They describe the setup there. They had a 40 kilowatt output radar. And what was the frequency is in here. Frequency isn't super critical to the discussion. It was chosen for a reason. There it is. 30 megacycles per second. There it is. 30 megahertz.
It's very
30
familiar. with it.
megahertz. So anyway, the big deal is how long it took. This took between 960 seconds and 1,000 seconds for the signal to come back. This is the signal that they got back. They sent a sawtooth signal like that. See that? And then these are time delayed. So that's what they got these back. Pretty cool. They got these amazing echoes back. And you can see these shapes here. Not perfect. No measurement is perfect. These shapes are not the shapes that you get normally from the sun. They only get these shapes when they are sending their radio signals to the sun, and then they come back bounced with that same pattern. So yeah, see this? You know, of course, there's some noise bursts and things at times, but look at that. These nice patterns. Amazing.
Nice. You get some noise bursts. You get some data. You get some iterative. Well, let me stop sharing so you can talk. No volume. Okay.
What a goof.
You got to put it back.
Oh, all right.
Although I have one more video of Toby doing neural network noise. When we're talking about noise, we'll get into that in a second. But yeah, so here's the paper that Toon doesn't read but likes to reference and hosts at mctoon.net/sun all the time. Or he went over it loosely with the solar radii. Now he didn't go over. I mean, he had the same picture, but he went over this graph, and he didn't go over how all of this noise looks identical to the solar echo that they got between 0 and 3 here. The noise.
He moused over a noise burst and was like, "Look at how good this solar measurement is."
Now again, they know that they need to get a return.
Amazingly good.
Like the way this works is it's time dependent because the speed of light is fixed and the other one is fixed. So that they need the only thing they can manipulate is time. So the time it takes to them to get a quote return. Now, what determines a return? Well, when you build a giant receiver, I don't know, I forget how big it was, then you can, determine that return deduced via all this noise. It says there's so much noise, so many echoes that they know for sure that this was a real return. Again, they send out the super high powered signal at that frequency that McDoom couldn't remember, that had no bearing apparently. And they know that when they send it out, they get this return. So when they send this, it returns this. That's what they're saying, that the sawtooth signal. But they get so much generated static noise that isn't data because their receiver is so more sensitive than they'd ever need, that has ever been before, that their discernment at what constitutes noise and what constitutes a hard solar return from the sun within the specified date range is very nebulous at best. That is my critique of this paper. I think that there's so much noise here that their analysis is going to be pressed at best. Now, we compare it with, say, LIGO. LIGO had a detection, they were trying to detect gravitational waves. There was a public scandal, so to speak, where they were detecting noise and, or they had injected a noise signal that would be analyzed through their iterative neural networks that would be interpreted as a gravitational wave. But it turns out that was a fake signal interjected by the boss. And then it was a big mishap. And then later, like 2 weeks later, they had another signal that wasn't fake, that was totally real, that looked identical to the first one. And that's how LIGO was used to detect gravitational waves. And that was through a series of noise that they would sculpt to do pattern recognition against their data. So actually, I got one last video, and it's our boy Toby going over how LIGO was iterative layers of interpretive data based on returning a signal to get an absolute measurement of a gravitational wave. And the process is very much similar to how they use for the sun to return their radar signal within the specified time frame to get the bounce that they need. Nice. All right.
So yeah, they just go through there's essentially they've been building upon this concept of matched filtering. And what that implies is essentially that they're filtering for the data that they're looking for before they even look at any of the, before they draw any conclusions about the data. It's actually called noise. That's actually, then they take the noise and they run it through what's called a convolutional neural network. And the first layer of the convolutional neural network is extrapolate the data out across multiple dimensions and add spatiality to it across multiple dimensions. Then they go through and they look for certain shapes within that dimensionality, and then they do correlations upon all those shapes, and then they do combinations of those shapes to create new correlations. Then they go through and they remove spatiality from all that data, and then they do normalization. And so basically that's just throwing out a bunch of data. And then after they've done normalization, they do another whole layer of classification. And then after they've done classification, they run through another
layer of the network, the convolutional.
Yeah, it's just another layer of their neural network. Yeah. And so all that is to say, whatever they're measuring, could there be something they're measuring that relates to the sky? It's entirely possible, but whatever they're measuring comes through a computational statistical framework. And so they're not actually measuring anything direct. And so you have to really take everything that comes from LIGO with a grain of salt, because you have to understand it's all viewed through a purely theoretical, hypothetical relativistic lens. And so if anything falls outside of that, it's just like when they go to test for the Elias effect and they use an electromagnetic brake to make sure it doesn't actually go outside of what it's supposed to do. That's what they're doing here, but in a way more complicated fashion. They're just making sure that they don't get readings that go outside of what they're supposed to see, such as daily fluctuations and seasonal variance. So yeah, like, I wish that we could actually get the real data from LIGO and not just the what they get that comes out of a convolutional neural network. And then not only that, but just one last note on LIGO, the dudes, when they first measured it, like the next day or whatever, however long afterwards, it was revealed that the first data was like the first gravitational wave that they measured was actually sample data. And they were just like testing the engineers to see if they were going to find it or something, I guess. That came out. Like first they revealed it. First it was revealed to the world. We found gravitational waves. And then afterwards they're like, oh, actually, we didn't actually find them. And I'm almost wondering, like, did they just get caught? The fact that they planted data to make this happen, to the point that the second time when they measured the gravitational waves, you can go find YouTube videos of the guys that worked at LIGO, and they didn't trust the readings at all. They like went around hunting for thumb drives and like checking their network for bugs and stuff because they're like, did someone plant data again? Essentially is what I could gather. The guy literally didn't believe their like big groundbreaking massive gravitational wave experiment, the thing he like devoted his life to. He didn't even believe it for months because of like the psychological games they've been playing with those guys there. So like yeah, like I definitely would take everything from LIGO with a big grain of salt.
Right, so a lot of similarities there. Here we go back to audio. Window, no audio, cool. See, a lot of similarities to what Toby was saying with interpreting gravitational wave data from noise to what this paper was putting forth with their giant receiver that they also got back during the time that they were looking super hard for it. Don't forget, they needed a specific time signal to get within that increment to solidify their already known distance. So when that time interval came around, they were like, listen super hard, and they were able to depict this tiny signal in between all of this other noise that looked identical. That's what that paper's putting forth.
See that graph, gang? Just get back a frame. Guys, if you're going to take all this effort to graph your data, don't you think you should include dimensional units, amplitude, you know what I mean? And any kind of magnitude? Like we want some quantification of some kind here. Like, what is this amplitude? They're not going to tell you that. They're not. It's just.
Why would they?
Analysis.
Why would they hide it, Stone? Is the amplitude so low that if we saw the actual dimensions of that wave, we would be like, we would laugh?
You would see how direly inconsequential these dotted curves are. Yeah.
That is the thinking, right? If they were to actually quantify this would all have no meaning. As right now, they're trying to pretend that this does have meaning in between these noise bursts. I like how they at least illustrated and tagged, look, inconsequential, irrelevant noise burst, inconsequential, irrelative noise burst, actual data looks identical, more inconsequential noise, more inconsequential. And then they even go on to say, look, it looks identical, but it's for real, trust us. Anyway, moving along to our next paper. Our next scientific proof is one of our NASA papers called To See the Unseen, A History of Planetary Radar Astronomy. We're going to go through this a little bit. Famously, this guy's thesis was dependent upon returning the signal from the sun. So in this paper, showing how they did it triumphantly, at the end of it, he will for sure get that echo, because otherwise he wouldn't have gotten his thesis for it, right? His thesis was dependent on getting this echo. Now, what we're also going to see within this is another whoopsie where they thought they detected the first radar signal back from the sun, but through their iterative noise analysis process of the data, it actually was a false positive. It was just two signals that came back microscopically distant from each other, but were two distinct signals, and therefore not the single return they were looking for. So something that we just had Toby explain how first LIGO wave was so-called detected was an error. We're going to see the same thing with the first radar bounce back from the sun. And this paper is actually super long. It reads more like a book, so we're just going to summarize it real quick. He goes through the radar was the first prototype of planetary radar, maser amplifiers, and long-term time integrations to try and detect Venus echoes. Right? They invented their lab, not invented the lab. They tested it in the lab based on the lab results in 1959. 76-meter radio telescope. It was again corroborated by JPL, boys at the Jet Propulsion Laboratory over at NASA in Goldstone. They said they achieved the first unambiguous real-time radar detection in 1961. This is the big one. The big de facto announcement to the world, we got it, boys, pack it up, we're going home. That was 1961. Then they pretend to correct it a little bit with some Russian lads who pretended to get a slightly different number so that there could be some public contention so they could arrive at the new correct number today. So what we're going to go over, though, is some of the ways or the equipment you would need to detect this return signal amid all the network noise, rate of returns, false positive, and timing signals to be able to get this math to equal out to 1.5 times 10 to the kilometers, which is just 93 million miles. Again, they're able to just use D equals V times T to derive an astronomical unit. This is the modern interpretation of the parallax angle to how we definitely know the distance to the sun. And at first glance, it could be rather convincing, right? Because you're only using the only thing that you could really contest here is the time it takes to get the return signal, but unless you want to go over the speed of light, but it is relatively consistent to have the rate with the illumination or induction rate that's quantified be reproducible and corroborated to the point where it's dependable as an actual variable. So maybe not so lucky attacking this part of it, but we can attack this part of it, because then it becomes, well, how do you know that you got that return signal precisely when you said you got it? When you're building these giant, never before seen super sensitive receivers with giant parabolic dishes and going through super sensitive data that no one's ever seen to interpret a signal during the specific time frame that you need it to return.
So all they had to do is just look at the data set from the time that it would take for the transit to occur, and then looking at that section go, oh, look, the peaks line up. It's not just noise. It's exactly what we expect. And then by not showing the actual magnitude of the amplitude, they can just take any variation of the section of that time and go, look, we found it. It's right there, guys.
Yep. Like turn on your signal, wait 1,000 seconds, listen super hard for that time frame. And if you happen to see any noise that resembles a signal, that's your boy. Pack it up, move on. That would be how easy it would be to fake it. Say if you were disingenuous or financially motivated to find a certain signal, here's how one would scientifically quote find it with little objection. No one would be able to double check you.
Say the future of your career in education depended on it. Say your PhD candidature said no echo, no thesis. What would you do hypothetically?
And this goes over sort of my main critique to this, is that this radar echo method relies heavily on interpretive complex signals and cross correlation, which are subject to noise, signal processing artifacts, assumptions from the source and medium. Of course, we're using the speed of light in a vacuum. We're bouncing it not in a vacuum to a sun across, space or whatever. And either model, this thing's filling that distance. It's not vacuum, so this would be a correct speed. Thus, the distance would be skewed by the incorrect speed. It also doesn't account for what we know as C plus V, right? The speed of light isn't constant. It's subject to the velocity of the energetic medium in which it's traveling, and it has an east-west component. So taking into account that fact, this would also throw this simple calculation way off, because it's dependent on the constant C of C. Now, the biggest objection is how they interpret their data, right? When you need to get that return within that signal, and you have super highly sensitive receivers that the average man can't replicate into levels of data noise that no one's ever seen, because it's so super sensitive, it's bouncing off of every conceivable quote atom and particle in the geosphere is returning signals. And then within all that, they had this precise method to know exactly when, after this, based on atomic clocks, within the 300 seconds, they knew they could get that signal. And boom, when you know it exactly within that window, they received the signal that wasn't noise, that specifically correlated to this. So again, C plus V would totally break this whole scenario. It's just hard to quantify that, because they're using C not as a variable, but as a constant, right? As we're about to go over, there's some problems with the interdependency of the constants of physics, meaning that the constant should be independently derivable. They should have a value independent of the other constants. But what we're finding is since they're only used in conjunction with each other, they only have meaning with each other. They are themselves a set of interconnected variables, not a set of independent constants, as put forth by one of the papers we're about to go over. But here's a snippet from that paper we went over before that we didn't quite quote yet, which was the history of planetary radar astronomy by this guy, right? That no echo, no thesis guy. But a snippet we're going to pull from is one of the incidents, like the whoopsies. As Toby went over with LIGO, there was a false positive that they interjected themselves to fake everyone out. Then they publicly went, boys, we got it. We got gravitational waves. They're real. We've detected them. And then they had to go, actually, on second thought, one of our guys interjected some false data, and now we falsely detected that there really was no gravitational wave. And then later they had to go, oh, no, we definitely got it. It looks identical to last time, but this one's totally real. Trust us, gravitational waves are real. So again, the same thing happened here, as outlined in this paper. It's a chapter called "We Were Wrong," and he said, "Oh, we need the signal. My thesis depends on this. It's gonna get it." And we were looking real hard during that interval that we needed it to return, and we got super excited, and we misconstrued two pulses for a little wishful thinking, he says, and that's the same pulse. Pulled them together, ignored the difference, sat them one on top of each other. Boom! Told the world we had the wrong value of the astronomical unit, et cetera, et cetera, et cetera. So again, false positive, as before any of this happened, before the big in 1961, this happened in 1958, right? They had a famous false positive, and they went, boom, guys, we got it. Radar return, echo from the sun. Turns out, nope, we're retarded. None of that happened. We couldn't tell one signal from another because we're using super sensitive equipment. And then 3 years later, boom, same thing, signal. This was totally real. Trust us, boys. We totally found it. Moving on to another paper we pulled from NASA from 2003, from the JPL over at our boys at NASA Jet Propulsion Laboratory, and from Harvard. This one goes into the discussion on the relationship of the ratios of the constants of physics, how they determined the use of that to determine the astronomical unit with radar measurement, and then how the constants have been adopted and evolved. So they're saying that the selected group of constants, including solar parallax, the Earth-Moon mass ratio, velocity of light, Earth's radius, and others, how these are all interconnected and related. From the opening pages here, this is from a lad who's expressing consternation about the known values in physics being interrelated. They're not independently derived. They're related on each other. And as defined, they're supposed to be independent of each other, right? So he's a little bit upset about this. And he's observing here, he says, they used to have Newcomb, which is a different table of constants they were using before they redefined everyone. They've been reluctant to change the values of constants through several important inconsistencies are known to exist. And he says, actually, the value of a constant is never measured directly. It's only ever measured through a series of differential corrections, which we then employ. And the analysis of the discrepancies between the observations and the ephemeris yield corrections to the values of the constants in the ephemeris. So he's noticing that, hey, we're not adjusting the constant of the AU, we're affecting the published place that planet's supposed to be and using the AU instead. That's what they're updating instead of the AU being wrong. The constant can't be wrong.
Can you go back for a second? That's a direct quote. He's quoting directly from the explanatory supplement of the ephemeris released by the British Crown, where they talk about how they come up with all these derivations for everything. That's hilarious. I didn't even catch that the first time.
Yeah, he's quoting from this. Yeah.
Oh wow, that's such a good quote. Well, I know what I'm gonna do later. Get out my supplement to the ephemeris and get that quote. That's awesome.
That quote continues all the way down here. This whole thing is from the ephemeris.
Yeah, I didn't realize that the first read through. That is great. What a bunch of homies, just putting it out there for the boys. Like, so quick, for those who don't know, that would be the highest form of authority for them, regarding astronomy and where the positions of things are in globularity.
And they're just amending it.
I believe we're talking about the Royal Society boys. Are we not?
We ain't not. Yes, we are.
If during the period covered by observations, the value of any constant value has been altered, then the ephemeris at times before alteration is inconsistent with the ephemeris at later times, and an analysis that fails to take account of that change is bound to lead to erroneous conclusions. Wow. So hey, we've been adjusting this on the back end, and if you don't continue to do that, the rest of it falls apart too. Neat.
Oh man, that's so awesome. GG. It's a great find.
And then right in the beginning, his premise over here in chapter 2, he says about the system of astronomical constants. He says the fundamental constants of Earth consisting of the elements of its orbit, the mass, specifying size, shape, orientation, rotation, and inner constitution, along with the velocity of light, comprises the system of constants. And it's been called a system because it comprises the whole model of Earth, and that he's also arguing these actually are not independently derived. He says over here, an ideal system of constants would be one in which these theoretical relations were satisfied rigorously, while the adopted value of each individual constant agreed with its observed value within the limits of uncertainty of the latter. And then most crucially, this ideal has not been realized even today. So what he's saying is, boy, I wish these series of interconnected ratios were independently constant, and they're not. And they have never been, and they're not even today. That's another important quote from this dude at the JPL over at NASA about the fundamental constants, including the distance, shape, and size of Earth. So it's almost like a bunch of boys got together and decided on these values so that when used in calculations formulaically with each other, the ratios would always tie back out. Mathematical genius.
Quote, the math works, end quote.
Right. So if you had a bunch of lads who were trying to make math their reality, this would allow them to do that. Quite thoroughly.
We actually adjust our coefficients every year, though. So if you're using last year's ephemeris, you might be off by a little bit. You make sure you get your new copy.
He's also commenting that because they chose the constants, that they may be profitably revised based on the inclusion of the radar measurement distances, saying, hey, I notice you boys are messing with radar distances to confirm these, and that there may be profitability if we revise them as well. Interesting. And then, again, he's also commenting as an honest chap that, hey, even though the modern value of the speed of light is known to 6 figures, the uncertainty of light velocity and determinations is a single source of error in the radar measurements. Meaning he knows that if you go back to the math of d equals v times t, and when he put 300,000 kilometers per second or whatever, 300,000 meters per second as the speed of light, if that's in any way not precise, then that would throw off the so-called precise distance that you derive using that formula from those radar measurement experiments, meaning that all these would thus be even higher of a margin of error. And using that, he's actually rating these. He said, these are the good boys doing the radar ranging methods to get the precise measurements within, the margin of error. And these are the shitty boys doing the same thing to a lesser degree of specificity and not returning the proper value. So again, a basic summary of his critiques of the radar tools to quantify the constants. It's heavily relying on theoretical models, which is complex signal processing, which we couldn't hit on enough. I don't think that was with Toby's iterative neural networks. And when you're processing noise, using signal processing to turn noise into data, it's very tricky to not manufacture the thing you're looking for, especially with processes like that. And in fact, that's what they're designed to do. They are dependent on planetary orbits and ephemerises, which then gets changed based on observations of the constants not being correct. Dependent on the velocity of light not being c plus v, which in fact we know and can substantiate other ways indirectly through satellites, GPS, and through Dayton Miller's experiment of interferometry. Atmospheric and plasma effects. And of course, the other thing we haven't mentioned is they're aiming a giant radar receiver at the biggest conductor of plasma in the known universe that we know of to the sun, and they're looking at a tiny body behind it trying to reflect light. They're saying, hey, look at the radar returning from the tiny body of light that's returning, and definitely not from the sun. So atmospheric and plasma effects could be a factor in any and all of these measurements, signal returns, and data. The biggest one being the layers of data processing that they go through, which are actually heavily reliant on models. So they're doing fundamental relationships, systematic constants, AUs, radiuses. They're all of that data interpretation, and when they're getting it is based on all their models that they're trying to validate. And one last paper, I think, is the one where they try to get the radar ranging for the distance to Venus. Remember that our boy in the beginning knew some numerology and some black magic, but he knew distance, like he knew the size of Venus already. And now they're trying to corroborate that with actual radar ranging to see if he was right. They already know he was right, but now they're going to show how he was right using this super sensitive receiver. So this one's called the radar measurement of the planets of Venus. They use this giant, I think it's 85-foot parabolic reflector with this giant gain and a crazy amplifier to try and get the distance of Venus. So they're trying to look at it at the closest proximity. So at its Keplerian orbit, where it's closest to Earth, they're trying to aim their telescopes at Earth on it, and they're trying to get a return to get the distance in the same D equals V times T relationship. So they're also using open loop receivers with predicted Doppler local oscillator tuning. As our boy Brian pointed out last time we did this, that just means they're just pumping the signal range with which they're sending and receiving to an extreme where that's all they're going to hear and see. And this is the other parts of the setup that's so complicated with these giant components, radio wave amplifier. They have this IF amplifier, a mixer, actual oscillator, programmed local oscillator, the one that we were talking about, which is connected to the ephemeris Doppler versus time, and then all of these other components, the keying oscillator along with the phase shifter, also tied to the ephemeris for range versus time to get finally to the transmitter. And then they're using all of this to determine that actually, when we looked real hard through our iterative noise, we were able to determine a constant that we definitely returned a signal return within the bracket that would lead us to believe that Venus is exactly at this distance. So if you don't believe them, you can simply build a 86-foot parabolic receiver at a base in the desert yourself, and you can listen and you can hear what they heard apparently using this giant setup on your home backyard.
I've got almost all of it except for the phase shifter and the keying oscillator. If anybody has those two components, and also a recent ephemeris, I need an updated one of those. I'll find it for you guys. Oh, I got the dish already. I'm just missing those three components.
Obviously, this is super hard to replicate for any of us at home. That was the joke. No one's got to be able to build this to be able to hear what they hear to determine if it was noise or actual, return from the sun or from Venus.
I feel like if you gave Stone enough time, he could build one.
Just give me the budget.
We need some money. Yeah. This is just a quick inclusion from another paper from, I think, one of our Russian lads who made the same observation that I did. He said, hey, I see what you guys are doing with radar ranging and using D equals V times T, but because you're all relativistic lads and you guys think the speed of C is constant, I got some bad news for you. He was pointing out that actually, since we know it's not constant, all your errors would be introduced based on that. Now he's got some Russian diagram, but he's using the same diagram of Venus and where it would be based on its position in its elliptical orbit based on Kepler. And he's saying, hey, actually, you'd be wrong with the period of this because it would introduce deviations in the calculated distances that you measured by radar, which would change the values used in astronomy. And he said that those anomalies, if you were to correct that, would not be explained, and that you wouldn't be able to correct the position of planets formally to correct for these areas. You'd be making the other way. And he says, hey, that's probably corresponding to the radar data that you guys are screwing up. So I just thought that was cool. He noticed that a C plus V versus C would introduce errors increased by orders of magnitude into your radar ranging and distance equations, which is why he thinks that they're making adjustments to the ephemeris. So wrapping it all
Adjusting
up.
the old ephemeri to compensate for C plus or minus V, the classic.
Oh, dude, I missed the Jaren video. How did I forget to play the Jaren video? Man. I don't know if it's too late now. It's probably too late.
I mean, you can breeze through the basic concept of it because we already got the ratios down. So now you just multiply by another factor and it'll rescale all the distances proportionally. So you would see things traverse the sky in the same periodicity, but the physical distance that you would computate that to be relative to you would be different, but nothing else would change.
Yeah, that's pretty much it, right? I had a video by the flat earther formerly known as Jaren, which was for a while forming the baseline of my understanding of what scaling invariance was when you're constructing the whole models based on the angular size. And he put forth this video that explained it sort of really well and succinctly that I meant to play, but I think I rushed forward and ended up talking about it instead. But as Alan just explained, he went over how the entire solar system is actually built off of these contrived variables and ratios, and that in fact it's all for the sun specifically. It's based off the angular size of 0.53 degrees, which we also went over a little bit. But he also did this nice slide to show that look, it works for this distance and this diameter, but it also works for a bunch of other distances and a bunch of other diameters, right? So the main proof of the distance to the sun is the parallax formula and the angular size formula, where we use 2 times the distance over 2 or whatever it was. So this over here is just a product of it using the only known factor that you can't change, the apparent size, angular diameter 0.53 degrees, and it would also work for a sun this far away and this wide, et cetera, et cetera, et cetera. It also would work, say, for the a sun 3,567 miles away and 32 miles wide.
Works for the moon too, so the same angular size. And then
Yep.
and keep in mind here, so FE Core has a video where they took a zenith measurement of the sun transiting, and then they made a circle around it, and then put that next to that circle, so the sun would have to transit its own diameter again. And then taking the time that it would take for that to come out, it comes out to be 32 miles as well. And doing the radius of the celestial sphere that Brian derived from the eclipse stuff, you can do that to get the what the diameter would be as well, and that comes out to be about 32 miles as well. So like all we have is this angular size relationship, and if you do the trig based off of what you see and the time it takes for it to traverse that distance, you get this same dimension here. But to get different sizes and distances, you have to make the assertion that they're different sizes and distances based off of nothing. Like if you do it off just the components you have, you're going to get that 32 to like 37 number for everything. And if you do it off of whatever your cosmological belief is at the time, supplemented by unending changing coefficients every year, you can have these distances too.
Yeah, so I showed the math on how they use the angular size formula to get 93 million miles, but I forgot to show the math where you can use the same formula to get, actually it's 3,500 miles away and 32 miles across, as we went over in that video, right? So it's always the same. You can use the same formula to show the same math to get the same distance and the same size. So what the whole point of the video was that it was called covariant scaling, meaning that the whole thing is scaled off of the apparent size, because as you go further away, the diameter changes, right? That's what it is. And because if math is reality, then this whole thing would mean that they're all reality. And if you change just one of these, as we were showing with the derivation of the AU, then all the rest of them change. That's why they're frequently expressed in ratios of AU. Like, hey, Mercury is 0.4 AU, because that way they'll never be wrong. That way they'll always stick to Kepler's ratios without an underlying empirical quantification. And that way they'll never be wrong. This will always be right? So that's pretty much the germ video. I think I had...
You drop a link to your Prezie in the chat there?
Yeah. I think that's all I had. Decimal Z, went through this. One more paper? No, that radar ranging paper was the last one, plus our Russian brethren checking them on C plus V. And then I wanted to summarize that everyone who uses the distance to the sun is basing off of this 0.53 degrees, which could equally apply to all of the other distances. And of course, how they use it for that when they can easily use for this. And that is that's all I had for how they determine the distance to the sun.
Well done, lad. Some good finds in there. Really put some context to all the mathematical ratios they use to assert dominance of their cosmological model.
Yep, kicking some ass.
Well, what a young lad with no agenda who just wants to ask honest questions will show you, right? I bet this guy got fired and buried after this. I don't know. Listen to this. How dare you ask honest questions? What's wrong with you?
Suicided with a double shotgun blast to the back of the head.
Yeah, like, is he even still around, let alone writing papers?
So what happened was he was real depressed and he jumped out of his university library window. Even though he was known for not being depressed, being very energetic, lively.
There we go. Canva link for everyone.
Awesome. And I'll put that in the description for the lads later so they can get it. But yeah, definitely check out the slides there and then play that video from Jaren. It's a classic. It's by far the best breakdown that's been presented for that. Cool. All right. Well, with that, I think we are ready to wrap up. Were there any questions or comments in the chat? I did see a question for you, Shane, but I didn't want to interrupt you. Let me see if I can find it.
What is the distance to the sun? I don't know.
Yeah, that's what it was. It was how would you what do you think it is? Well, what we argue primarily is that if you're a globe lad, or if you want to use latitude and longitude and maps and stuff, the distance to the sun is 6218. Because that's just as good. That's going to create the 60 nautical miles per degree relationship necessary for you to use the coordinate system. So that internally consistent derived number would serve just as good as any other number, because as you move on the ground, you're going to see the sun change in proportional ratio to that.
That's the maximum distance that it would ever be, right? Yeah, exactly.
Yep. And then for all other purposes, it's just kind of role play. Like we went through the history at the beginning, where if you assert a different diameter and a different distance, you got a whole new number there, buddy.
When you say what do I think the distance to the sun is? All I know is it's 0.53 degrees in the sky. That's what I can tell you.
I would add extra depth to that. What you threw up a frame earlier on from Decimal Z where he did the Eratosthenes experiment in a digital fashion. And I give extra points to the Filipino team that did a couple of years before that in real on a large table with a bunch of nails all set at the preset heights, and they could check the angle and measure it on the board. But what's common about both of those is that in order to produce the sun effect from above, they used a convex bottom end lens. I don't remember what the top geometry was like to the lens, but the point is that it was convex on the bottom, and the actual distance from the sun to that lens cannot be known, because what we're seeing is the apparent position of that focal point.
Very good point.
Right.
Well
so
said.
we can't even dream to give them that answer, and I think they should stop fucking asking us for it. You know what I mean? That I'm a little irritated at their ignorance about the model that the flat earthers are presenting here and have been presenting for years, but the Globies are just not fucking paying attention. So, guys, it's not put up or shut up anymore. It's pay attention. And I think that's more relevant here.
Well said, Stone.
Yeah,
I like it when you
that's
get
great.
angry and break things down even more concisely than you do normally.
I gotta get quantified and kick some ass.
That's a very good
I
point.
I think that's definitely called for in this scenario here.
I also didn't know that some other team did it before Decibel Z with a table quantifying it. Like, was their conclusion? Look at the radius of my square table. Like, look at the precision with.
They measured the
actually,
radius of the square table.
Even in their analysis, they did a bit of a digital setup in what they wanted to show you to do with their empiricals on the table, and they mentioned how when you try to measure the absolute position of the sun through triangulation of 3 different points on Earth at the same time, give or take your use of spherical geometry to ascertain your actual distance between those 2 points are not relevant. The point is that they are very far apart, hundreds to thousands of miles apart, all seeing the sun simultaneously at the same time. And when they do, that those angles do not intersect at any singular point. That you draw 3 angles, and you know what I mean? You do not actually produce a coherent position of the sun due to the errors between them.
How do you fix
And
that,
because of the
Stone?
apparent position.
How do you fix that?
You
Do you just move it to 93
can't fix
million and say that they converge at infinity?
Yeah, you move it to a near infinite distance away. That's exactly how you fix that. No, good point, Alan. Good point.
Yeah.
Good point.
Yeah.
But no, I think it's entirely relevant that obviously these attempts have been made, not just by this Filipino team, but I also saw another North American, German/European team, and I think a couple of people in the UK also participated, and they all tried to do the replication of what I just mentioned. And they were, from what I remember of this YouTube video years ago, was that they had constant battles trying to deal with that particular observed empirical error. That the angles just did not agree with one another. That you could not actually plot the literal triangulated position of the sun because it's a focal point, it's an apparent position, and it's different for everybody on Earth at any particular moment.
Yeah, it's like trying to plot a rainbow together or whatever. Like, what do you see?
Exactly like trying to plot a rainbow's position. Yes, just like that, with a secondary offset.
Now, I heard that if you do plot the position of a rainbow and you go to where it's at, there's a pot of gold at the bottom.
Yeah, there's a
of it?
leprechaun sitting right there laughing at it,
And-
taking so long to get there. Stupid yellow card! Will they ever be learning around here? I think not, buddy.
Within that leprechaun pot of gold is the actual height of the sun above flat Earth. So if you get there, you can give the rest of us the hint or whatever.
It gives you a choice: pot of gold or the known actual physical distance.
All you do is chase the rainbow, and you two could have the answer.
Nice. All right, lads. Well, I think we'll wrap up on that. Fantastic breakdown, Shane.
Thank you, boys. Good times. Thanks to Tune for showing up exactly and doing the Globe Steel Man the weakest way. We just how we like it. Here's this paper I haven't read. Go look at it. Duh, love it. We love to attack arguments with that level of empiricism.
It's awesome, dude. All right, so next Sunday we will have Stone G presenting on his method that he was trying to get presented to the recent Dr. Shiva thing using plane radar to measure the lack there of curvature for the ascent angle of a plane. Is that kind of what was going on there?
Also known as an ILS glide scope experiment. Yes.
Oh, the ILS glide scope experiment. So yeah, Stan's going to be breaking that down. And so that'll be awesome. And that actually has a long, extensive history to it, starting with
Years of epic saga.
Starting with the
Yeah.
original claim from Eric Dubé using a level or a phone level or whatever on a flight or
A
something like
spirit
that.
level.
Something
Bring
like
it
that.
on
Yeah.
the flight.
So we're going to go over the
Direct models.
entire we'll go over the entire history of that and then using their own landing radar system against them. So should be awesome.
Nice. Looking forward to that one.
And Monday, of course, will be Celestial Theodolite update number 27, hosted on my channel at space_audits. That'll be at 8 p.m. Eastern. Then Tuesday will be Ether Cosmology Roundtable 110. It's a big number there. We're getting up there. And then Friday, of course, will be the Twitter community night. So we've got the whole week plotted out. We'll see you guys next week all the way to Sunday.
Yeah.
Cool.